All right, let's dive into one of the biggest, most important upgrades happening to the internet right now, even if you can't see it: post-quantum cryptography. Yeah, I know, it sounds super complex, but really it's a story about keeping everything we do online safe from a wild, new kind of threat.
Just think about that for a second. Every password you've ever made, every single bank transfer, every private message, it's all protected by what's essentially a digital lock. But what if those locks weren't permanent? What if they all had a secret expiration date?
Well, that's the exact problem we're facing with the rise of quantum computing. And believe me, this isn't science fiction anymore. It is a very, very real challenge that some of the smartest people on the planet are racing to solve as we speak.
Okay, so before we can really get the solution, we have to understand the threat. What is it that makes a quantum computer so different?
Here's the thing. This isn't about just making computers faster. It's a completely different way of thinking. You see, the computer or phone you're using right now uses bits. They're just little switches, either a 1 or a 0, on or off. Simple. But quantum computers, they use qubits. And a qubit is a total game changer because it can be a 1, a 0, or somehow both at the exact same time. This weird state, called superposition, just unlocks a level of computing power that normal computers can't even touch.
And that really gets to the heart of the matter. This new kind of power means that math problems we think are practically impossible to solve today, problems that would take the world's best supercomputer millions of years, could become ridiculously easy for a quantum computer to solve.
And here's the scary part. The hard problems that our entire system of digital security is built on, they happen to be the exact kind of problems that quantum computers are perfectly designed to crack.
Our most common types of encryption, things like RSA and Diffie Hellman, they work because they're based on math that's just way too hard for normal computers to do, like taking a massive number and trying to find the 2 prime numbers that were multiplied to create it. But for a quantum computer, with the right algorithm, it can shatter these unbreakable problems like glass.
Now, I know what you're probably thinking. This all sounds like a problem for way, way off in the future. But the danger? It's actually right here, right now.
Right? I mean, if these super powerful quantum computers aren't really a thing yet, why is everyone in such a hurry? Why are we worried about this today?
Well, the answer is this really chilling strategy called harvest now, decrypt later. It's pretty simple. Attackers are stealing huge amounts of encrypted data today, right now. They can't read it yet, of course, so they just store it. They're hoarding it, waiting for the day they can get their hands on a powerful quantum computer. And the moment they do, boom. They can unlock all that old data. That means any sensitive info. Think government secrets, corporate plans, your private data. Anything that needs to stay secret for years to come is already at risk.
So yeah, the threat is big, it's real, and it's urgent. But here's the good news. The world's cryptographers are not just sitting around waiting for everything to break. They're already building the next generation of digital locks.
Say hello to post-quantum cryptography, or PQC. This is basically a whole new toolkit of encryption that's designed to be safe from attacks by both the computers we have now and the quantum computers of the future. And here's the most crucial part. These new security tools are built to run on the classic computers and phones and servers that we all use every single day.
Okay, this is super important because it's a point that gets a lot of people confused. Post-quantum cryptography is not the same thing as quantum cryptography. What we're talking about, PQC, is all about creating new software for the computers we already own. Quantum cryptography is something else entirely. It's a method of communication that uses quantum physics. It's cool stuff, but PQC is the practical solution we need to upgrade the entire internet.
So how does PQC actually work? Well, it basically swaps out those old vulnerable math problems for brand new ones that we're pretty sure are tough for both classic and quantum computers to solve. It's like we're rebuilding our digital security on a bunch of new, much stronger foundations. We don't need to get into the weeds of the math, but the new approaches involve things like lattice-based, code-based, and hash-based cryptography. The main takeaway here is diversity. We're not just betting the farm on one single new type of lock.
And this is not just some theory being kicked around in a university lab. This is happening. The world is actively gearing up for what is going to be a monumental upgrade to our digital lives.
This is a massive global effort. You've got organizations like NIST in the US that have spent years holding a worldwide competition to find and standardize the absolute best new algorithms.
And all over the world, industries from banking to tech are starting to plan out this huge migration. And what's the top priority? You guessed it, protecting our most critical long-term data from that harvest now, decrypt later threat.
All right, so let's just quickly boil this all down. First, powerful quantum computers are coming, and they pose a massive threat to the encryption that protects us all today. Second, post-quantum cryptography is the answer. It's the new set of tools for today's computers to fight off tomorrow's attacks. And finally, this switch to PQC isn't some far-off idea. It's absolutely necessary, and it's already started.
So we've seen the threat, and we've seen the solution that's on its way. But that leaves one huge question, right? How? How does a quantum computer actually unravel the math that keeps a system like RSA secure? We are going to dive into the incredibly clever algorithms that make it all possible in our next explainer. I'll see you then.